In part 5 of the Unit 8 notes, we are going to be covering collision theory, factors affecting reaction rate, and limiting versus excess reactants. Collision theory is a theory which states that atoms, ions, and molecules must collide in order to react. However, not all collisions lead to chemical reactions. For a chemical reaction to occur, particles must collide with the correct orientation, and they must hit with enough force or energy for a change to occur. The minimum amount of energy that reacting particles must have to achieve a reaction is called activation energy. In our picture below, we have nitrogen monoxide and ozone reacting in a few different ways. On the top, we have ineffective collisions. So this could be instances where the activation energy was too high based on the energy that is actually present, or the molecules could not have the right orientation when they collide, so they just bounce off of one another. In our effective collision on the bottom, these two molecules must have hit with sufficient force, and they also have a better orientation so that this part of the molecule, this atom, can detach and combine to make the nitrogen dioxide. In this example, we have hydrogen and oxygen gas combined inside of a balloon, which is shown right here. The gases do not react with one another until a flame is brought into contact with the side of the balloon. Explain why the flame is necessary using scientific terms. So when these two gases interact with each other normally, there must not be sufficient energy in order for a reaction to occur because the balloon is not exploding. But when you bring the flame in, that little amount of heat is the activation energy required in order to kickstart this reaction. As the reaction continues, the flame is going to heat up the other molecules that are around and is going to continue this reaction until it goes to completion. So activation energy was necessary in order for this reaction to occur. Factors affecting reaction rate. Collision theory explains why a chemical reaction may or may not occur, but what about the speed at which a chemical reaction occurs? The reaction rate can be manipulated using a variety of factors which can either speed up or slow down a chemical reaction. For this checkpoint, we're looking at the reason why a scientist might want to speed up a chemical reaction, and there's a variety of reasons why they might want to do that. A reaction might occur too slowly to actually see, so maybe they want to be able to see the reaction, or maybe they're trying to create products in an efficient manner because they need the product for some reason. Maybe they're trying to sell it if you're thinking about something like pharmaceuticals. Okay, next we're going to be going over some of those factors that can impact the reaction rate. First, we have temperature. Increasing the temperature of a chemical reaction results in a higher rate, while decreasing the temperature results in a lower rate. When reactant particles are heated, they move faster, which results in a greater frequency of collisions. Collisions will also occur with greater frequency due to the increased energy and are more likely to achieve the required activation energy from products. So by adding heat to a group of chemicals, we can have them react faster, and by decreasing the heat, we can have the reaction occur more slowly. Next up, we have concentration. An increase in concentration of one or more reactants results in an increase in the reaction rate, while decreasing the concentration will decrease the reaction rate. We know from collision theory that chemical reactions are going to occur when particles collide with one another. So if you have an instance where there are more possible collisions, like when things are really closely packed together, then reactions are more likely to occur. Pressure. When the pressure of a gas is increased, its particles are forced closer together, which decreases the amount of empty space between the particles. This is essentially the same as increasing the concentration. Decreasing the pressure is going to have the opposite effect. So if your chemicals are gases, you can increase the pressure to make them react faster, or you could decrease the pressure to make them react slower. Surface area. An increase in the surface area of a reactant will increase the rate of a reaction. Surface area is larger when a given amount of a solid is present as smaller particles. In order to increase the surface area of a substance, it may be ground into smaller particles or dissolved in a liquid. In our example here, we have magnesium ribbon reacting with hydrochloric acid, and then magnesium powder reacting with hydrochloric acid. The magnesium ribbon you already saw in our demo earlier in the year. So this was the metal that I burned, and then it lit up very brightly. Now, if I were going to grind that up into a fine powder first, it will react a lot more quickly. So increasing surface area will make reactions occur much quicker. Catalysts. A catalyst is a substance that increases the rate of a chemical reaction by lowering the activation energy without being used up in the reaction. In biology, you might have seen these referred to as enzymes. After the reaction occurs, a catalyst returns to its original state, so catalysts can be used over and over. So that means that a catalyst is not actually part of the chemical reaction taking place, it's just something that's present that helps the reaction to go faster. Since it is neither a reactant nor a product, a catalyst is shown in the chemical equation by being written above the yield arrow. So you can see that in the example here. If you were to do an elephant toothpaste demo, you would have hydrogen peroxide. You would add in a catalyst. Here we're using manganese oxide, and then you would make water and oxygen gas. But this reaction occurs so quickly so that if you have soap or anything else that foams inside of it, you have this little column that's going to shoot out of the graduated cylinder. An inhibitor is essentially the opposite of a catalyst. It is a substance which slows down reaction rates or prevents a reaction from occurring at all. Some inhibitors block lower energy pathways and thus raise the activation energy. Others react with the catalyst and destroy it or prevent it from performing its function. In the food industry, inhibitors are called preservatives or antioxidants. They can reduce the effectiveness of a catalyst. In this checkpoint, we're going to be looking back at Teenage Mutant Ninja Turtles 2, The Secret of the Ooze. The Turtles battle two vicious mutants, Tokka and Razor. The only way to defeat Tokka and Razor is to trick them into eating anti-mutagen cubes hidden inside of some donuts. Carbon dioxide is a blank for the chemical reaction, but Tokka and Razor keep burping, which is releasing carbon dioxide. In order to speed up the process, the turtles use fire extinguishers to administer a high concentration of carbon dioxide. The mutation is reversed, and we get one of the greatest songs in history, Vanilla Ice's Ninja Turtle Rap. Now, based on the context here, it looks like we are trying to speed up the chemical process. So based on that, I would say that this is going to be a catalyst. The carbon dioxide is not actually used up within this chemical reaction, but is helping it to occur faster. Limiting versus excess reactants. A limiting reactant is the reactant which limits the extent of the reaction and therefore determines the amount of product which can be formed. A limiting reactant is the one which will run out first during a chemical reaction. It is not necessarily the one that you have the least of, because sometimes things are used up at different rates. So that's something that you're going to have to be careful of. An excess reactant is any reactant or reactants that are left over when a reaction stops. In a chemical reaction, any reactant or ingredient that you had more than enough of will be considered an excess reactant. In the example shown below, we have a situation where we're making hot dogs. So you need hot dogs and you need a bun. So here we have 5 hot dogs, but we only have 4 buns. So since these are used in a 1-to-1 ratio when you're preparing a hot dog, the buns would be the limiting reagent or limiting reactant. Reagent and reactant mean the same thing. So you can make 4 complete hot dogs, which we can call our theoretical yield, which means that we have 1 leftover hot dog without a bun, which would be our excess reagent or excess reactant. In our checkpoint example, we are trying to figure out how many bicycles can be built based on our number of ingredients and also what the limiting reactant would be. So you can consider this kind of like a chemical equation. We know that in order to make a bicycle, you need 1 frame, 2 wheels in order to make that one bicycle. Now, the way you should think about this is if you had one of your ingredients and more than enough of the other, how many finished products could you make? So we're going to go through 2 examples here. So if I had 100 frames, and I know that I need 1 frame for every 1 bicycle, I know that just based on the frames, I would be able to make 100 bicycles. Now, what if I started with the wheels? So I have 120 wheels, and I have more than enough frames. For a bicycle, I know that I need 2 wheels. So 2 wheels for every 1 bicycle. So that means that I would only be able to make 60 bicycles. Whichever one of these 2 ingredients can make less product, which would be this one, that must be your limiting reactant. So the limiting reactant in this one would be the wheels. How many bicycles would you be able to make? Well, once I've made my 60 bicycles, I would run out of wheels and I would no longer be able to continue making bicycles. So I would have leftover frames. The reason why I chose this example is to show you that even though I had more wheels initially, that was not the excess reactant. It actually ran out first, because for this particular reaction, the wheels were being used at a greater rate. So that concludes our Unit 8 notes. These are all the topics that you should be familiar with at this point. I just want to remind you of some of the resources that you should be using when you're working towards getting ready for the Unit 8 test. Of course, you have all of the practice assignments that were posted on Kia, including this one right here, which is your chemical reactions test review. Now, it is your responsibility to not only complete all of these assignments, but also to make sure that you understand the content from each of them. So if you do particularly poorly on any of these assignments, you need to make sure that you are asking me questions. You also have labs for this unit. This one here is the FET balancing lab, which we had our 3 levels for. So if you did not really understand that assignment or you didn't do particularly well on it, that's another thing that you need to seek out help for so that we can get you adequately prepared for the Unit 8 test. Finally, just like with all of our other units, I've picked out a bunch of videos from different content creators and added them to my playlist under Unit 8. So for this unit in particular, we have videos from Tyler DeWitt, Melissa Maribel, Crash Course, and TED-Ed. Some of them might be assigned to you in class as Kia assignments, and some of them might just be optional. So if you're having trouble with any of the content from Unit 8, make sure that you check out those channels.